Testing, testing. Okay, this video is going to be on the photoelectric effect. I will link to some of the resources I've used in this video in the description. The photoelectric effect is observed, and it's one of the arguments for the photon theory of light, or the particle theory of light. It's observed that when light is incident on a metal, electrons are emitted off the metal, and using a gap in a circuit you can actually measure the current of these. Some particular things of interest is if the light has a frequency that's too low, the photoelectric effect is not observed, regardless of the light intensity, how bright it is. What is also noted is that if you shine a light of a higher frequency and the photoelectric effect is already observed, then you end up with photoelectrons, the electrons coming off the metal, which have a higher kinetic energy. We'll go through and we'll show this, and we'll explain some of the reasons for that, how it links to the photon theory of light. First of all, it's a reminder. There we go. Let's remind ourselves about metallic lattices. What makes metallic lattices special is the way they bond. They bond by sharing the valence electrons, which get released into what we call the sea of electrons, or delocalized electrons. Delocalized electrons are not bonded to any particular atom, but are bonded to the metallic lattice as a whole. They are free to move between the cations, as shown here, but they're still bound to the metal, so it still requires energy to release them. How much energy depends on the metal itself, as we'll come to see by the photoelectric effect. Okay, so what frequency is required to release electrons from the metal is a property of the metal, of the element of the metal. Okay, so if we measure that in terms of energy, so shown here, we can see a chart that demonstrates that reactive metals have a low work function being the minimum energy required to observe the photoelectric effect, and precious metals, non-reactive metals, have a higher work function. Okay, so we'll demonstrate this. Now this application is one that's offered by Phet, which I'll show you the website. Again, link in the description. Okay, oopsies. There we are. So interactive simulations. And this is nifty because we can actually observe the electrons moving past in real time. So I've decided to start with my target is going to be copper to start off with. And I'll show you this. So let's turn the lights on. So we are now sitting at the threshold of visible and ultraviolet light. And let's see if we observe anything when we turn the lights on. Okay. So let's turn up to about 50% intensity. And we are not observing any photoelectrons traveling past. So let's increase the frequency now and see what happens. So by decreasing the wavelength, you increase the frequency. Okay. Still nothing. So we're getting, there we go. So the lowest frequency or longest wavelength where photoelectrons are emitted is called the threshold frequency. Now, if I increase the intensity, this doesn't make the electrons travel any faster, but it does mean there is more of them traveling past. So you end up with an increase in the current. You can see here, if I decrease that, I decrease the current. I'll just increase the frequency a bit. Okay. So I can turn that down. So long as I'm meeting the threshold frequency, I can turn that down, and I'm just getting more, less electrons. If I turn it up, I'm getting more electrons. All right. So let's go to something a little bit more reactive. Okay, so let's go to sodium. Sodium's being the most reactive metal I've got here, and we can see we're getting electrons traveling a lot faster, and there's a lot more of them. Okay. And we can go much lower And we're still observing, so now in the visible spectrum, we're still observing the photoelectric effect. Let's see how far we can actually go. So let's go to blue. Yep, we're still seeing electrons travel past. Let's go to green. And we still see electrons traveling past. I'm going to stay on green for now. Okay. Keep that around 50% intensity. Now, to measure how energetic these electrons are, we can apply a voltage to retard the electrons. As the electrons are slowing down. I'm going to turn this, I've actually gone a little bit too far. We're going to turn this such that electrons are just getting past. Now, I can't do too much fine tuning on this application. You can see we've got electrons that are traveling very close to the other end, but not quite making it. Okay. So remember, voltage is the potential difference, and it's related to energy. It's the amount of work done per unit coulomb. So we can actually measure the voltage of the energy of these electrons coming past by working out how much voltage we have here to do to stop these electrons. Okay, so we've stopped all the electrons, they're not reaching the other side. Let's just see if intensity has any effect on that. Can we get those electrons to travel past by increasing the brightness? No, they're still all stopping. Also notice that some are stopping earlier than others as well. Okay, but if we were to increase the frequency, so now we have current happening again. So we need to increase the voltage to stop those. So as you increase the frequency, the electrons have more energy and you require more voltage to stop them from traveling across. All right, now I've actually got some data that was gathered by students at the Melbourne Synchrotron. So let me show you this data. Got all my notes in the wrong order. There we are. Okay, so this is an Excel file, and we can see a few things on here. Why don't we just increase this for the sake of video quality? Maybe a bit more. Okay. So measuring the effect of intensity using a single wavelength, we notice that as we noticed with our simulation, regardless of how bright the light is, it's approximately the same amount of voltage required to stop the most energetic electrons from traveling across. All right, but let's have a look at if we vary the frequency, what effect that has on the stopping voltage. Now, these students have gone and carried out some measurements of wavelength versus the amount of voltage required to stop the most energetic electrons. So I'm going to start by carrying out the averages for them. All right. Yep, let's do that. Okay, so let's average these values. All right. So these are the average voltages required to stop photons of, stop the electrons emitted by photons of these particular wavelengths. So notice that these are all visible wavelengths, so we have a very reactive metal. We've actually calculated the frequency here as well. All right, probably should round those off, but let's do that while we're here. Remember where to do this. All right. There we go. There we go. All right, so we've rounded off the scientific notation. So there's a frequency as in, so frequency increasing, wavelength decreasing. Frequency increasing, the amount. Okay, these results are not actually particularly, oh no, there we go. Yep, they are actually, the voltage is increasing. Now, because we are stopping electrons, the voltage required to stop the electrons has the same numerical value as the energy in electron volts. So these are actually the same number, but this is representing voltage. And because it's the voltage used to stop electrons, the energy is the same in electron volts. To get this to measure in joules, we need to times the electron volts by the charge of the electron, 1.6 times 10 to the power of negative 19. Okay, so now we have this value in joules. Again, I think we want these numbers in something else. Okay. All right. I'm going to have to format these ones as well. And some to notation. There we go. Okay. So now we've got energy in joules. So let's go and see if we can generate a graph. I'm going to generate a graph of frequency versus maximum kinetic energy and see what happens. All right. So I'm just going to try this. It's been a while since I attempted doing something like this, but let's give this a go. Oops. There we go. All right. All right, that's not working. So let's just do this. I'm going to do this a different way. Get back over here. All right, format our numbers again. Number. Okay, now they're both in science. Oh. Okay, format, number, scientific. Good. All right, so let's graph the two of these. Let's do a scatter plot. My x-axis. And let's delete that one. Okay, there we go. I'm also going to do a couple more things. Put some zeros on there, minimum value 0. And we're going to do all right, doesn't mind me doing that. But I'll demonstrate what I'm trying to do anyway. Let's just go with 0. Okay, so we can actually see here, we get an increase in maximum kinetic energy of the photoelectrons for an increase in the frequency. It's a linear graph. If we work out the slope of that, we can actually determine Planck's constant, which is a h value. All right, so let's have a look at that. Let's see if we can do that. Series. All right, so I'm going to have a trend line, linear, and I'm also going to have an equation. Okay, and if we look at the slope for this equation, 6.69 times 10 to the minus 34. That is very, very close to 6.63 times 10 to the minus 34, which is your value for h, Planck's constant. This value over here will actually be your work function in joules, or approximately, because that's the y-intercept. We can't actually see the y-intercept on this graph, but if you try and take that line back, you can see it will be going further and further. So this is the minimum energy required to release any electrons from the from the metal, and that's called the work function. So the work function of I think whatever this happened to be was approximately 3.11 times 10 to the minus 19 joules. And if you estimate the value here, this little point, the x-intercept, is the threshold frequency, because this is the first frequency around here where the photoelectric effect would have been observed, because now we've got actually positive energy up here. Before that, you see no photoelectric effect down this part of the graph that we can't see right now. So let's just go through and talk about some of our observations. So I've got a few slideshows for this. Okay. So the photoelectric effect, first observed by Heinrich Hertz, and known as the Hertz effect. So Hertz observed and then showed that electrons illuminated to ultraviolet light create photoelectrons. It's been obscured. A photoelectric effect refers to emission or ejection of electrons from the surface or jelly of a metal in response to instant light. Now, we're just going to say metals because we're not going to confuse with ionization. The photoelectric effect is the release of delocalized electrons by the presence of visible and ultraviolet light and beyond. To get ionization of atomic electrons, you need something more powerful, high-end ultraviolet or X-rays or gamma rays. Okay. For the photoelectric effect, electrons are emitted from matter, metals, non-metals. Actually, we'll just stick, as I said, we can stick with our metals for now in our definition. All right, electrons emitted in matter to transferred as photoelectrons. Photoelectric effect requires photons with energies of few electron volts to over 1 MeV for high atomic metal elements. All right, Einstein's equation of photoelectric effect. So you can see some of the key terms we've mentioned in our discussion. W is a work function, which the minimum energy required to remove a photoelectron from the metal. So if it's given the given metal, h times by the frequency. E is the maximum kinetic energy of electrons, and m is the rest mass of the ejected electron. Okay. So with these graphs, if you were to graph two different metals, you'd see two parallel lines with different threshold frequencies, but they'll be parallel because they both have a slope of h, which is Planck's constant. Okay, so that's been cut off. That's meant to be a W there. K max equals hf minus the work function W. All right, so to show you a couple more slides just to explain the explanation of the photoelectric effect. Okay, so the photoelectric effect observations. So you can see here actually some of the some different metals and their graphs of frequency versus electron kinetic energy, or maximum electron kinetic energy in particular. For cesium, lithium, and silver. So obviously, in this case, the more reactive the metal, the higher the electron kinetic energy, and the lower the threshold frequency. The kinetic energy of photoelectron is independent on light intensity. The kinetic energy of photoelectrons for a given material depends on the frequency of the light, and if the frequency is below the cutoff frequency or work function of the metal, then it is not observed. So you can determine the work function by continuing this line backwards until it intercepts with the y-axis. That is the amount of energy required for that particular metal. Okay, some other observations. When the photoelectrons are produced, their number, not the kinetic energy, is proportional to intensity of light. So when we increased the intensity, we saw more electrons, but they were stopped with the same amount of energy. Also, the photoelectrons are emitted almost instantly following illumination of the photocathode, independent of the intensity of light. So even if you had a dim light, photoelectrons can emerge from that dim light, so long as the frequency is beyond the threshold frequency. Okay, so that's the idea here. Light of low frequency does not cause current to flow at all, and the current flow increases when, so it rises up as soon as the frequency of light, the threshold frequency of light is met. The electrons start to flow across the gap. So this is not well explained by the wave theory of light. Okay, so Einstein's explanation that won him the Nobel Prize, it goes as follows. So he applied Planck's quantum theory that light is emitted in packets called photons, and each photon has an energy of Planck's constant times by the frequency of light. So on a one-to-one basis, a higher frequency photon will have more energy than a lower frequency photon. The photoelectric effect arises when photons of light are striking the surface, the transfer energy to electrons. The energized electrons can overcome their attraction to the nucleus and can escape the surface, but only if the photon provides enough energy. But I'm compacting this a bit further. An electron can only escape if the photon, so it's a one-to-one basis. So you can't have a series of photons giving energy.
The photon is a type of
Thank you, Siri. So you can't have many photons give the energy to electrons to make it escape. And that's the principle that shows that low frequency light, regardless of intensity, may not create the photoelectric effect if it's below the threshold frequency. Okay. So here's some of the features not explained by the classical wave theory. No electrons are emitted if the incident light frequency is below the cutoff frequency. The maximum kinetic energy of the photoelectrons is independent on light intensity. It does increase the current, but not the maximum kinetic energy, as observed. The maximum kinetic energy of photoelectron increases with increasing light frequency, so you need a higher voltage to stop those electrons if you have a higher frequency. The maximum kinetic energy depends only on the frequency and the work function. So the frequency is how much photon energy, and the work function is how much the electrons are bound to the metallic lattice. So if you have a very reactive metal, you have a very low work function, and you have a very high frequency, then you have very high maximum kinetic energy of the electrons. Electrons are emitted by the surface almost instantaneously, even at low intensities. Okay. So, just to finish up, in Einstein's explanation, a tiny packet of light energy called a photon would be emitted when a quantized oscillator jumped from one energy level to another. Photon's energy equals hf. Each photon can give all its energy to an electron in the metal. It can't give some, it must give all or none. The electron is considered to be in a well of height W, which is called the work function of the metal. Now it can be bound more than W. W is the minimum amount. The maximum kinetic energy of the liberated photoelectron is the photon energy minus the work function. Alright, we're going to conclude the video here. Hopefully that has helped your understanding of the photoelectric effect.